just collected, Kathy and Ian and I recently, were looking at how pre-service science teachers portray what a scientist is. So we said, draw a picture of a scientist. This is what you get, a whole lot of. But where is that coming from? It comes from movies, it comes from TV. It's what they see when they're trying to draw that stereotypical scientist.
Most teachers would start a science class asking this question, what is science? Which is not an easy question to answer. And many science teachers can't answer that question. And teachers will often ask this of their kids, and if they don't ask it of their kids may be asking them. The general public, when faced with a decision on something that's scientifically based, is not going to run out to the garage and do an experiment. What's more important and much more realistic is for them to understand how the scientists came up with that claim, what was their evidence, what are the limitations of that evidence, how does it fit in with what we currently know about the world, and it's an understanding about inquiry and an understanding about science that is much more practical in terms of producing an informed citizen.
That being a scientifically literate society is a very important thing. That's one of the ideas I know Judy was bringing up to you, that we need people to understand good information from bad information, to be able to discern those things when they're on the internet.
Supposedly will put the general public in a position to make more informed decisions on scientifically based issues they face every day.
They have to be informed voters. They've got to take care of their family members as they age. They have to know how to make good decisions about their health care.
Should I eat McDonald's hamburgers because that cattle is really full of a lot of growth hormones so they can bring them to slaughter quicker, to things like should I go to suntan places and all those things.
So it's not just about whether they're going to be scientists one day, it's are they going to be able to navigate their way through a scientific society that we have today.
How many things have we put together perhaps in a way that's perhaps incorrect only because we've never seen something like another arrangement before.
All the things in science that we know or think we know have a lot of data to support it. There have been a lot of investigations, a lot of people agreeing on these things, but we never know if we have all the data. We may return and look at that same data in a different way in another year or two, and so it may change. Or we may get better technology that allows us to make observations and measurements that we could not make before. Putting together ideas to come up with scientific concepts, laws, theories, etc., is an act of creation, a mental act of creation, putting things together in certain ways. Creativity is not a bad thing. In fact, most of the big ideas, like those revelations we were talking about earlier, were single acts of enormous creation. We want students to know what an observation is. We want them to know what an inference is. We want them to know that all scientific knowledge has a little bit of both. And inference is not a bad word. Inferences are okay if they're consistent with the data.
I've got my college pre-service students who say, well, my bean plant is dead. Is that an observation or an inference? Well, it's dead. It's an observation. I'm like, no. You're observing. The leaves are now dry. The leaves are crunchy. The leaves have fallen off. The stem is wilted. Those are all your observations. You're putting all those observations together to make a really good inference that your bean plant is dead.
We're not advocating that you be subjective. We're saying that you're a human being. You have different backgrounds, you have different biases, you have different things you want to see, and that's where your subjectivity comes in. Science tries to protect itself from subjective things, and that's why we have all these little checks and balances in the studies we do and in the professional community. But scientists are human beings and they're subjective to a certain degree. They believe in a particular interpretation rather than another, partly for subjective reasons.
We have theoretical commitments in our head that drive the way we interpret our evidence.
I mean, when you start finding these patterns and relationships, it's your mind that's inferring these connections. You've created these patterns, okay? You're inferring what this card looks like because it is the one that makes the most sense in the pattern that you created.
It's not that we're saying you should be subjective, we're saying it's unavoidable. Theories and laws, probably among the most misunderstood words in the scientific vocabulary. The thing we're trying to get away from is kids believing that theories change the laws. And the theories are somehow drastically imperfect knowledge, and laws are somehow perfect knowledge.
Laws are statements of patterns. They're often mathematical. These are observable things. This is very much tied to observations. You can observe the relationship between objects in our environment and develop laws that describes those relationships, whereas theories are inferential. They are the explanations behind those.
If you look through the history of science, there's never been an instance of a theory changing into a law. Depending upon what it's a hypothesis about, it could go the direction of a law or the direction of a theory. Laws and theories need to be consistent with each other. And the laws and theories that we hold affect the observations that we make.
The society and the culture in which we live as scientists directs the kinds of questions that we ask. It directs the way we ask those questions, the way we investigate those questions. And
science is socially and culturally embedded. Science affects the culture and the society that it's in, and it is affected by the science, by the culture and the society it's in. Conclusions must be consistent with the data collected. I would always get students saying, well, we have no conclusions, we didn't get what we were supposed to.
Yeah.
But you didn't get what you were supposed to.
Yeah.
You got what you got and explain it. Scientific data and evidence are not the same thing. And it's a very, very important point. Scientists collect data. Then they process that data and think about it, analyze it. And then the data become irrelevant, become supportive of a hypothesis, or become challenging of a hypothesis.
Scientific progress is very messy. You start, you stop, you revise, you go back, you test again, you manipulate, you go back. You do all of this stuff for months and years and sometimes, and when you're done, you present a nice little paper, here's what we found. They don't show you all the messy stuff that went into getting there.
You can teach kids to do things, but they have no idea why they're doing it. And this knowledge about inquiry is for them to be able to reflect on what they did, to be able to understand why they did it. I mean, the idea is that maybe kids will do these things better if they know why they're doing it. And when you're teaching things in the context of nature of science and knowledge about inquiry, it's much more engaging instruction. They appreciate the knowledge much better. They realize that they were partly in creation of that knowledge from that activity. And that's a much more empowering thing than just memorizing what I say is the authority up here. Nature of science and inquiry are best learned through explicit instructional attention, as opposed to the assumption that if you just do science, you'll somehow come to those understandings I had up here. You need to teach it like anything else.
It may be that you don't want to hit on all of them every time. It could be, gee whiz, I haven't had subjectivity that I could bring out in any one of these activities that I've just done. I can really illustrate it here. And so you hit on that one.